What if a single idea could change the world? What if three friends in a city pulsing with energy could spark a revolution that would transform everything we know about technology? It's 1993. The tech world is, well, a very different place. The internet is just starting to become a thing for most people. Computers are big beige boxes. They're useful for spreadsheets and word processing, but honestly, they aren't exactly exciting. Gaming? Well, gaming was mostly happening on dedicated consoles like the Super Nintendo. PC gaming existed, but it was a niche within a niche. The graphics were blocky, the experiences were limited, nobody was really thinking about creating realistic three-dimensional worlds on a personal computer. It just seemed too far-fetched, almost like science fiction. But in a small diner in San Jose, California, three friends were about to change all of that, forever. These three friends were Jensen Huang, Chris Malachowski, Curtis Preem. They were all engineers who had seen the inside of the tech industry. They worked at companies like Sun Microsystems, LSI Logic. They understood the trajectory of computing power. They saw where things were heading. And they noticed a huge gap in the market. They realized that the standard computer processor, the CPU, was a jack of all trades. It was designed to do a little bit of everything, but it wasn't a master of anything specific. This was especially true when it came to handling complex visual information, the kind of processing needed for graphics. The conversation at that Denny's wasn't just casual chatter, it was a brainstorming session that would lay the foundation for a multi-trillion-dollar company. They believed that graphics weren't just a small part of the computing experience. They saw a future where graphics would be central to everything. They imagined a world where computers could create immersive, visually rich experiences that would captivate users. This wasn't just about making games look a little better. It was a fundamental bet on the future of computing, a bet that visual computing was the next major wave, and they decided they were the ones who were going to build the hardware to ride that wave. Their initial idea was simple but incredibly ambitious. They wanted to create a specialized processor, a chip designed specifically to accelerate graphics. This chip would offload the heavy lifting of rendering images from the main CPU. By doing this, it would unlock a level of visual performance that was simply impossible with existing hardware. They believed this would create a new market for what they called accelerated computing. It was a bold vision. It was a risky vision. They were essentially creating a new category of product from scratch, and they decided to name their new venture NVIDIA, a name derived from the Latin word invidia, meaning envy. It was a fitting name for a company that aimed to make products everyone would want. So, what exactly was this problem they were trying to solve? Think about how a computer draws something on your screen. Side by side, a blocky low-polygon 3D character from a 90s game and a modern photorealistic game character. In the early 90s, this task fell almost entirely on the central processing unit, or CPU. The CPU is the brain of the computer. It's a general-purpose processor, designed to handle a wide variety of tasks one after another, very quickly. But creating three-dimensional graphics is a very specific, very demanding job. It involves millions, even billions, of tiny calculations every single second, just to figure out the color and position of every pixel on the screen. Asking a CPU to do all that work is like asking a world-class sprinter to also be an Olympic weightlifter. It's just not what it's built for. The result of this limitation was clear to anyone who tried to play a three-dimensional game back then. The graphics were slow, they were choppy, frames would drop, making the game feel sluggish and unresponsive. The worlds felt empty and were made of simple shapes and flat colors. This wasn't because game developers weren't creative, it was because the hardware was holding them back. The CPU was the bottleneck. It was trying to manage the game's logic, the AI of the enemies, the sound, and also draw the entire world on screen. It was simply too much for one chip to handle effectively, and the visual experience suffered immensely because of it. NVIDIA's founders saw this bottleneck as an opportunity. Their big idea was to create a different kind of processor, one that worked in parallel, instead of having one or two powerful cores that did tasks sequentially. Their chip would have hundreds, and eventually thousands, of smaller, simpler cores. All of these cores would work together at the same time on a single task. This approach is called parallel processing. It's perfect for graphics because rendering an image is an embarrassingly parallel problem. The calculation for one pixel on the screen doesn't depend on the calculation for the pixel next to it. So, you can have thousands of cores all calculating pixels simultaneously. This new type of chip would be called the Graphics Processing Unit, or GPU. It was a revolutionary concept. The GPU would work alongside the CPU. The CPU would still handle the general tasks of running the operating system, and the game's logic. But when it came time to draw the world on the screen, it would hand that massive parallel task over to the specialist, the GPU. This division of labor would free up the CPU to do what it does best, and it would allow the GPU to do what it was designed for, processing massive amounts of visual data at incredible speeds. This was the key insight that would unlock the future of gaming and so much more. With a clear mission and a groundbreaking idea, NVIDIA was officially incorporated on April 5, 1993. Jensen Huang took on the role of CEO, a position he still holds today. Chris Malachowski, Curtis Preem, brought their deep engineering expertise to the table. They started with just $40,000 in the bank. It was a humble beginning for a company that would one day have a market capitalization larger than the GDP of many countries. Their first office was a small space in Sunnyvale, California. It was the classic Silicon Valley startup story. A handful of brilliant people in a small room fueled by coffee, ambition, and a belief they could change the world. The early days were not easy. The company was entering a crowded and competitive market. There were already dozens of companies making graphics chips. Many of them failed. NVIDIA itself almost went bankrupt. Their first product, the NV1, was not a runaway success. It had some innovative features, but it tried to do too much. It combined graphics, audio, and a game port all on one card. It was also based on a different type of rendering technology that developers weren't eager to adopt. It was a tough lesson, but a valuable one. They learned they needed to focus. They needed to do one thing and do it better than anyone else: accelerate three-dimensional graphics for the PC. The turning point came in 1997 with the release of the Riva 128. This was the product that put NVIDIA on the map. It was a huge leap forward in performance. It offered the power of an arcade machine on a single chip for your home PC. It was fast, it was affordable, and critically it was embraced by game developers and PC manufacturers like Dell. This success gave NVIDIA the momentum and the cash it needed to keep innovating. It established a rhythm: new, more powerful GPUs every couple of years, consistently pushing the boundaries of computer graphics. With the Riva 128, NVIDIA had proven there was massive appetite for high-performance graphics. They had created a product gamers and PC enthusiasts desperately wanted. They had also established the brand as a leader. But this was just the beginning. Gaming was the first application for powerful parallel processing engines. Their vision extended far beyond making games look good. They were building the engine for a new era of computing, and the world was just starting to take notice. The foundation was laid for a revolution. With their vision clear and their company formed, NVIDIA's founders hunkered down to build their first product. The challenge was immense. They weren't just improving an existing technology, they were trying to create a new category. In 1995, they unveiled their first chip, the NV1. This wasn't just a graphics accelerator. It was an ambitious, all-in-one multimedia solution for the PC. It packed two-dimensional graphics. It packed three-dimensional graphics. It included a 32-channel sound card. It even had a port for Sega Saturn controllers directly on the board. The idea: turn a boring office PC into a full gaming and entertainment machine. A bold, everything-in-one marketplace. The NV1's 3D tech was unconventional. Instead of the now standard polygons, tiny triangles that form modern 3D models, NVIDIA bet on quadratic texture mapping, a more complex way of drawing curved surfaces. Jensen Huang and his team believed it was superior. They partnered with Sega to bring arcade games, like Virtua Fighter, over to the PC using this tech. They hoped it would become the new standard, but the NV1 was a commercial failure. The market wasn't ready, and NVIDIA miscalculated. While they pushed proprietary quadratic rendering, Microsoft pushed a new standard: DirectX. DirectX offered a common set of tools so games worked on any compatible card, and DirectX was built around polygons, not quadratic surfaces. Developers flocked to DirectX, simpler, with Microsoft's backing. NVIDIA and the NV1 were left on the outside. The all-in-one approach backfired. It made the card expensive and complex. Most users already had sound cards. They didn't want another. The NV1, brilliant engineering, but no clear market. A painful, vital lesson for the young company. They'd bet on the wrong technology, and it nearly cost them everything. The failure of the NV1 hit NVIDIA hard. The company had poured its limited resources into a product the market just flat out rejected. They were running out of money, and fast. By late 1996 they were down to their last 30 days of cash. Bankruptcy wasn't just a possibility, it actually seemed inevitable. This was the first major crisis for the company, a moment that would really test the resolve of its founders. Imagine the pressure in that small office. The entire future of their dream was hanging by a thread, and the clock was ticking down with terrifying speed. In this desperate situation, Jensen Huang had to make some of the toughest decisions of his career. He gathered the entire company and laid out the stark reality of their situation. Layoffs were unavoidable. They had to let go of more than half their staff, a heartbreaking move for any founder. The remaining employees were asked to work without pay for a month. It was an incredible ask, a true test of their belief in the company's mission. This period forged a culture of resilience and loyalty at NVIDIA. It was, in every sense, a trial by fire. The biggest decision, however, was a technical one. They had to abandon their beloved quadratic rendering technology. But they had to face the facts. The industry was standardizing on Microsoft's DirectX and its polygon-based rendering. To survive, NVIDIA had to pivot. They had to build a new chip from the ground up, one that was fully compatible with DirectX. This meant throwing away years of work and starting over. It was a humbling admission of defeat on one front, but it was also a strategic retreat that would allow them to fight another day. With a new laser-focused mission, the remaining team at NVIDIA went into overdrive. They had one last shot to build a product that would save the company. They had a single, clear objective: build the world's fastest DirectX-compatible 3D graphics accelerator. Everything depended on this next chip. Out of the ashes of the NV1 and the company's near-death experience rose the Riva 128. Launched in August 1997, the name stood for Real-Time Interactive Video and Animation Accelerator. The 128 referred to its 128-bit memory interface, a technical specification that, at the time, signaled some serious performance. This was the chip that NVIDIA bet its entire future on. It was a complete departure from their previous strategy. It was lean, focused, built for one purpose: to deliver blistering 3D graphics performance for PC games using the DirectX standard. There was no sound card, no fancy controller ports. It was just pure, unadulterated graphics acceleration. The Riva 128 was an engineering marvel for its time. It integrated a 2D graphics accelerator, a video accelerator, and a powerful 3D core all onto a single piece of silicon. This was actually a first for the industry and made it incredibly efficient. More importantly, it was fast. Really fast. It blew away the competition, offering performance that was previously only seen in expensive arcade machines. It could render millions of textured, lit polygons per second. For gamers, this meant smoother frame rates, higher resolutions, and more detailed game worlds. The market reaction was immediate and explosive. NVIDIA had learned its lesson. Instead of fighting the standard, they embraced it and executed better than anyone else. PC manufacturers like Dell, Gateway, quickly signed on to use the Riva 128. The company went from the brink of bankruptcy to shipping over 1 million units in the first 4 months. It was a spectacular turnaround. The success of the Riva 128 not only saved NVIDIA, but also firmly established it as a major player in the graphics industry. And its successor, the Riva TNT-2, NVIDIA, was on a roll. But their next move would change the industry's vocabulary forever. In 1999, they prepared to launch NV10. It featured hardware transform and lighting, or T and L. Before this, the CPU had to do heavy math to position objects and calculate lighting in a 3D scene. Hardware T and L moved that workload to the graphics chip, freeing up the CPU. It was such a monumental leap that NVIDIA needed a new name. This wasn't just another graphics accelerator, it was a new class of processor. They coined the term Graphics Processing Unit, or GPU. They marketed the GeForce 256 as the world's first GPU. The GeForce 256 was a massive hit. It delivered realism and performance previously unseen. Quake 3 Arena, Unreal Tournament, now ran with complex lighting, detailed models, and high frame rates. This moment ended NVIDIA's early struggles and began their dominance. By defining the GPU, they set the debate's terms. Competitors weren't just building cards, they were trying to build GPUs of their own. The GPU's invention completed their early puzzle. They had survived near failure, found focus with Riva 128, and with the GeForce 256, given their creation a name and identity to propel tech into the 21st century. For years, NVIDIA was the undisputed king of gaming graphics, but they were still seen primarily as gaming hardware. Then, around 2012, something completely unexpected happened. A group of researchers at the University of Toronto, led by Geoffrey Hinton, entered an annual AI image recognition contest. Their AI model, named AlexNet, crushed the competition. It was so much more accurate than anything that had come before it, that it shocked the entire AI community. It was a big bang moment for modern artificial intelligence. The secret to AlexNet's incredible success wasn't just a clever new algorithm, it was the hardware they used to train it. Instead of using traditional CPUs, the researchers used two NVIDIA GeForce GTX 580s. They realized that the type of math required for training a neural network, multiplying huge matrices of numbers over and over again, was structurally very similar to the math required for rendering three-dimensional graphics. This discovery was a complete game-changer. Suddenly, a tool designed to make video games look prettier was revealed to be the most powerful and efficient engine for training artificial intelligence in the world. NVIDIA's CEO, Jensen Huang, quickly realized the magnitude of this breakthrough. He famously bet the farm on this new direction. The company began to pivot. They started referring to themselves not just as a graphics company, but as an AI company. This was the beginning of NVIDIA's second act. The AI revolution might have been sparked by a gaming GPU, but it was enabled by a software platform NVIDIA released in 2006. This platform is called CUDA. Before CUDA, programming a GPU for non-graphics was incredibly difficult. It was a dark art. You had to trick the GPU, pretend your math was graphics. CUDA changed everything. It was a software layer that gave developers direct access to the GPU's raw parallel power. When the deep learning boom happened, CUDA was already mature and ready. TensorFlow, PyTorch were built on top of CUDA, making it the de facto AI standard. This gave NVIDIA a huge head start. That software moat was as important as hardware leadership. By creating CUDA and giving it away for free, they unlocked a universe of applications: scientific research, drug discovery, financial modeling, artificial intelligence. It was a brilliant move that made NVIDIA's platform the default for solving the world's hardest compute problems. As the AI revolution took hold, the demand for GPU computing power exploded. This, in turn, led to the rise of cloud computing giants: Amazon Web Services, Microsoft Azure, Google Cloud. To train AI models at scale, they installed tens of thousands of NVIDIA GPUs. NVIDIA saw this shift coming. They launched a new product line, starting with the Tesla series, built to be installed by the thousands in server racks. The data center business exploded from almost nothing to rivaling, then surpassing, gaming revenue. Every time you use an AI service, a language model like ChatGPT, a recommendation engine on Netflix, a photo tagging feature on social media, you're likely hitting an NVIDIA GPU in a data center somewhere in the world. NVIDIA became the essential hardware provider for the cloud, the picks and shovels of the AI gold rush. Instead of just selling the chips, they decided to build the entire computer. In 2016, NVIDIA introduced the DGX-1, the world's first AI supercomputer in a box. The DGX systems became the gold standard for serious AI development, used by every major AI lab in the world: OpenAI, Meta, DeepMind. While NVIDIA was conquering the data center, it was also setting its sights on another massive industry, ripe for disruption: transportation. The dream of a self-driving car is, at its core, an AI problem. The company created a new platform called NVIDIA Drive. They partner with hundreds of automakers and startups, from Mercedes-Benz, Jaguar Land Rover, to a new generation of electric vehicle companies. At the center of NVIDIA's story is its co-founder and longtime CEO, Jensen Huang. He is, honestly, one of the most recognizable figures in the tech industry. One of the most defining stories of Huang's leadership came during the company's near collapse in 1996. This experience forged a culture of resilience and loyalty that persists to this day. The company's success was built on the foundation of its engineering culture, a culture shaped by its other co-founders, Chris Malachowski, Curtis Preem. A famous anecdote, Jensen Huang's kitchen table analogy: senior leaders define the why. They trust world-class engineering teams, the cooks, to figure out the how. One of the most powerful, yet least visible elements of NVIDIA's internal culture is a principle Jensen Huang calls intellectual honesty. This is the practice of confronting the unvarnished truth, especially when it is painful or inconvenient. If you were to pinpoint one company that sits at the absolute epicenter of today's most important technological trends, It would be NVIDIA. Think about the biggest shifts happening right now. At the core of every single one of these revolutions, you will find NVIDIA's GPUs and software, doing the heavy lifting and making it all possible. This central role is most obvious in the field of artificial intelligence. The company holds over a 90% market share in this critical space. This means that nearly every major AI breakthrough is directly reliant on NVIDIA's technology. Beyond AI, NVIDIA's influence permeates countless other industries. In scientific research, in the financial sector, in media and entertainment, NVIDIA is not just a chip company anymore. It has evolved into a full-stack platform company. This platform strategy is most evident in their newer initiatives like Omniverse. It allows companies to build and test digital twins before creating them in the real world. From a conversation in a Denny's diner to the engine room of the global AI revolution, NVIDIA's journey is one of the most remarkable stories in the history of technology. They started with a singular focus on making video games look more realistic. The parallel processing architecture they perfected for pixels turned out to be the perfect architecture for artificial intelligence. When we look ahead, the trends are clear. AI will become more integrated into every aspect of our lives. Virtual worlds and digital twins will change how we interact, and autonomous machines will become commonplace. The company's next chapter is already being written. Initiatives like Omniverse, their push into robotics with the Isaac platform, and their relentless innovation in chip design. The story of NVIDIA is a powerful lesson in the power of a long-term vision, the importance of building a software ecosystem, and the courage to bet the company on a future that others can't yet see. What started as a quest for better pixels has become a mission to solve intelligence itself. The company didn't just change gaming, it provided the engine that is now allowing us to build a new world, one powered by accelerated computing and artificial intelligence. The green logo, once synonymous with gaming performance, now represents the very fabric of our technological tomorrow. And based on their track record, the next act is likely to be even more transformative than the last.